And we'll now move on to the second talk of the session, which is by Besfort Shaya of the University of Oxford on the probabilistic zeta function of a finite lattice.
Okay.
So over to you, Besfort.
Thank you very much. So I'll be talking about the probabilistic zeta function of a finite lattice, and I'll dive right in. So let's start with some motivation. I'll assume that we're all familiar with basic group theory and probability. If we are given a finite group G and S a non-negative integer, then we ask, what's the probability that a uniformly randomly chosen S tuple of elements of G generates G? And this is something that people were looking at, and essentially due to a generalized Mobius inversion procedure introduced by Hall in 1936, P of GS admits a finite ordinary Dirichlet series expression of this form. So we have a sum over all subgroups of G, and then we have some Mobius numbers on top, which are coming from this generalized Mobius inversion, which is really completely analogous to the usual number theoretic Mobius inversion. And then in the denominators, we have these group indices. So perhaps it doesn't matter if you don't know what an ordinary Dirichlet series expression is, but I just want you to keep in mind that on top we have these Mobius numbers, and then in the denominator we have some integers to the power of S. So the right-hand side of PGS actually makes sense for all complex numbers S. So we define the reciprocal of PGS as a function of a complex variable S to be the probabilistic zeta function of G. And the reason for this is that the reciprocal of the Riemann zeta function, at least for non-negative integer values of S, has a probabilistic interpretation. Namely, it's the probability that S randomly chosen integers are co-prime. Furthermore, we have this very nice identity relating the reciprocal of the Riemann zeta function with a product over all primes of the probabilistic zeta function of the finite cyclic group ZP. So a big question is, can P of GS be recovered from some combinatorial or topological structure associated to G? This is a question that Brown was looking at in the year 2000, and he ultimately answered the question in the affirmative by defining a probabilistic zeta function for lattices. Now, the goal of our project was to take this probabilistic zeta function for lattices and study it in its own right without necessarily relating to the probabilistic zeta function of a group. So just to make sure that we're all on the same page with what a lattice is, for the purpose of this talk, a lattice will be a partially ordered set, so a set L with a partial order, such that for any two elements x and y in L, there is a unique supremum for x and y with respect to the partial order, which is denoted like this and called the join of x and y, as well as a unique infimum denoted like this and called the meet of x and y. So perhaps it's helpful to look at an example and an anti-example. So this poset here, given by its diagram, is a lattice, and that's very easy to see, and it's perhaps the simplest lattice that you could get, which is non-trivial. And then we also have this poset here, which is not a lattice, because there is no well-defined supremum for A prime and B prime, since C and D are both upper bounds, but you can't compare C and D. So a similar combinatorial or probabilistic setup as for groups yields the notion of the probabilistic zeta function of the finite lattice, where again we have some Mobius numbers on top, and then we have these indices which are coming from the join irreducible elements of L. So these are the elements of the lattice which can't be written non-trivially as a join of two other elements. So in the case of groups, we allowed all elements of the group to generate, whereas for lattices, we're going to only allow join irreducible elements to generate, and the notion of generating is simply taking the join of a specified number of elements. So in this sense, join irreducible elements serve as building blocks for lattices. So J here is the set of all join irreducible elements, and Jx is the set of join irreducibles below X. And then I've introduced this bracket notation to just denote the ratio of the total number of join irreducibles and the number of join irreducibles below X. We inconsistently refer to this as the probabilistic zeta function fel rather than to its reciprocal, but we choose convenience over consistency here. I should also mention that our setup and definition actually differs slightly, but is a natural extension of Brown's original one, but I won't go into any details of how the definitions differ here. So a natural question is, how does the probabilistic zeta function of a finite lattice relate to that of a group? And Brown showed that if you take a finite group G, take all its subgroups, take all the cosets of all subgroups, put them together, add the empty set as an artificial bottom element, so smallest element of the lattice. So this is called the coset lattice of G, and Brown showed that if you plug in the coset lattice of G in the definition of the probabilistic zeta function for a finite lattice and shift the parameter S by 1, then you get back the probabilistic zeta function of the finite group G. So as I said, our purpose was to shift from the group theoretic setting and just study the probabilistic zeta function for lattices in its own right. So one natural thing to do is to move from the coset lattice, where you take all cosets of all subgroups, to the subgroup lattice. And we'll look at the subgroup lattice of a very nice group, so Zn, the finite cyclic group Zn, which is just isomorphic to the divisibility lattice of all divisors of n. If we denote by omega n the number of prime divisors of n counted with multiplicities, then we have this expression for the probabilistic zeta function of the divisibility lattice. Now, a special case of that is when n is square free, and in fact, in that case, we get a lattice which is isomorphic to the Boolean lattice, namely the lattice of all subsets of 1 through R ordered by inclusion. So in that case, the expression simplifies quite a bit, and we can actually express it in terms of the Stirling number of the second kind, where the Stirling number of the second kind with parameters S and R counts the number of partitions of the set 1 through S, which have R parts. And this is actually a nice connection to combinatorics, but it's actually expected. And if you just solve the problem of generating combinatorially, then the Stirling numbers appear quite naturally there. But perhaps a little bit more interestingly, this means that when you shift back to the non-square free case, you get a sort of potential generalization of the Stirling numbers of the second kind to a certain setting of counting f-tuples. So for a finite group G, we saw that if you plug in the coset lattice of G, then you get an ordinary Dirichlet series, meaning that the denominators all look like an integer to the power of s. And this is essentially coming from Lagrange's theorem, saying the index of a subgroup, the index of a subgroup in a finite group is always an integer. But this need not be the case when you move to lattices, since this index actually, it's just not necessarily an integer. And we observed in the example before that the index here is r over k, and as k ranges from 1 through r over k is typically not going to be an integer. So one question is, when you move from the group setting to the lattice setting, how much changes? And in this regard, we define a lattice to be strong coset-like. So we want to say that it sort of resembles a coset lattice. if these indices, these ratios of joint irreducible elements are natural numbers. Now, this actually, in principle, need not be a necessary condition to have an ordinary Dirichlet series because we have these Mobius numbers on top, and usually they alternate in sign. So it could happen that the Mobius numbers on top just happen to cancel out in exactly the right way to eliminate some non-integer ratio. So we define a lattice L to be weak coset-like merely if its probabilistic zeta function is a finite ordinary Dirichlet series. And we actually don't know if these two notions are equivalent, since we haven't been able to find any weak coset-like lattices which are not strong coset-like. But we do have some results on some specific examples. And first of all, we looked at the partition lattice. So this is the lattice of all partitions of 1 through n ordered by refinement. Then pi n is weak coset-like if and only if pi n is strong coset-like, if and only if n is small. So in this case, less than or equal to 4. And this is actually a very easy result to prove, and it's expected because the structure of the joint irreducibles in the partition lattice is very additive. And we don't expect addition to behave nicely with respect to these divisibility conditions. Perhaps more interestingly, this provides us with an example, namely pi 4, of a strong coset-like lattice, which is not isomorphic to the coset lattice of any finite group. Again, this is very easy to show, but a less obvious question is whether pi 4 embeds appropriately into a coset lattice. And appropriately really needs to be carefully defined here. Merely being a sublattice or anything weak like that certainly doesn't work. And we've actually proposed the notion of an appropriate embedding, but even under that notion, which is relatively simple, it seems to involve quite some interesting group theory to prove or disprove that pi 4 embeds into a coset lattice. Afterwards, we switched our attention to the d-divisible partition lattice. So this is the lattice of all partitions of 1 through dn with parts of size divisible by d. And they're, again, ordered by refinement, but then we don't have a smallest element in the lattice, so we just add in the empty set as an artificial bottom element. Now, there are several reasons to expect the d-divisible partition lattice to behave more nicely. The most basic one is that the structure of joint irreducibles in the d-divisible partition lattice is actually quite different from the structure in the partition lattice, and the structure there is a lot more multiplicative. So we expected that we would have some positive coset-like behavior here. But it turns out that that's not the case, and we have this very concrete result in the two-divisible partition lattice, saying that the two-divisible partition lattice is strong coset-like if and only if n is less than 4 or n is equal to 5. And in the general case, we showed that asymptotically, the d-divisible partition lattice is not strong coset-like. So when n is large in terms of d, then the d-divisible partition lattice fails to be coset-like. I certainly won't go through the full proof. I just want to mention the key ideas of the proof of this last theorem. So it actually reduces to investigating this divisibility condition of central binomial coefficients. And when d equals 2, we use Nagura's theorem on the existence of a prime in the interval from n to 6n over 5 when n is large enough. In this case, n needs to be greater than or equal to 25. And then we extract a prime p such that it divides the left-hand side, but not the right-hand side. When d is greater than 2, then we use the prime number theorem to find primes in suitably short intervals contained in m to 2m. Of course, they need to be a lot shorter than that to extract a prime p, which again divides the central binomial coefficient on the left, but not the one on the right. So I haven't given all details here, and there are some differences in how you should isolate and extract these primes depending on the parity of D, but this is essentially the core part of the argument. So I'll just finish off by saying that where we want to go next is to sort of better understand this tension between weak coset-like lattices and strong coset-like lattices, and perhaps get a very nice and concrete characterization of coset-like lattices. I'll stop here then. Thank you very much.
Thank you. That was a fascinating talk. It's always nice to hear about maths which is still going on and where we don't know the answers to some of the questions. The question about the weak coset-like, strong coset-like equivalence, we don't know whether they're equivalent. Do you have any, is there a general view that they are probably equivalent or probably not equivalent, or do we just have no idea?
I think that someone really needs to get their hands on a computer and try to compute some probabilistic zeta functions and see what's happening there. I haven't done that, but my feeling when I try to construct examples of weak coset-like lattices which are not strong coset-like, so I got the feeling that they actually might be equivalent, because whenever you start with something and then you try to just twist it a little bit, then you either realize that what you end up with is actually not a lattice, or you realize that you've completely sort of changed the structure of joint irreducibles and actually also made it strong coset-like in the process of making it weak coset-like. So I'm really not sure. I don't have enough computational evidence to say anything, but from trying to construct examples by hand, it does seem that they might be equivalent.
Thank you. Are there any other questions for Westford? I'm trying to keep an eye on the chat and looking for hands up, but I'm not seeing anything. In which case, thank you very much for another fascinating talk.
Thank you.
And again, audience, please show your appreciation by applauding.